I'm going to start talking about 12.3, rectilinear kinematics. In this case, erratic motion. So non-continuous motion, essentially. Okay, here's an application where velocity is given as a function of position. All right, and the question is asking to determine the acceleration at a particular position. If we take a look back at what we previously covered in a previous section, the equation we're actually going to use would be this one, right? We don't have time in the equation. The two variables are velocity and position. Okay, in this case, velocity is given as a function of time, and we have three intervals to look at, okay? So we also have an equation for that one, and the equation would be here. So we're looking for a position. So this now has velocity as a function of time, where we would perform the integration here, and then we have the positions defined. That way we could find the positions from this. Okay, so here's another example. In this case, the train's position is a function of time. Okay. So depending upon what we're looking for, if we're looking for velocity, in that case, it's just the derivative of the function of ds dt. And just in general, for the slope is essentially the derivative of this function, and the integral is the area under that curve. Okay. Okay, so if you were given the position versus time graph, you can actually determine the velocity at any point in time. And really, it's just the slope of the line tangent. Okay, and this gives you some, kind of a quick example of this, right? So if you're looking for the initial velocity here, you'd evaluate the derivative at time t equal to 0 of the position. The position function, the derivative of the position function with respect to time at t equal to 0. And then you do the same thing up here. You evaluate it at this time, for whatever this time is. You could determine the velocity at that point. So you could go through here and determine the velocity at any point along this, or any point in time. Okay. So from that, you could actually, from what you saw for here, you can actually use that to plot out the velocity versus time function. Okay, and this just gives you an example of this one. So we could follow the same process if we're given a function as of velocity. If we're given velocity as a function of time, we can now determine the acceleration. So the acceleration is just going to be the slope of this curve, or the slope of the tangent line of this curve at the individual points. From that, you could actually create curve acceleration as a function of time from the individual points, just like what we previously went over in the previous slide. Same idea, except now we're starting with velocity as a function of time. We're creating the acceleration as a function of time curve. So we can also go in the other direction. So given acceleration as a function of time, we can find the curve of velocity as a function of time, right? Now, this is going to give you like whatever the change in velocity is, right? So the area under this curve is the change in velocity of this function. So if you're starting with some initial velocity and you have some acceleration up to some point in time, let's say if we're looking at it at point t1, that's just going to be the area under this curve, essentially represents the delta v on the velocity curve. Okay. In another case here, the acceleration is given as a function of position, right? And this, as part of the equation or the information that's in the equation, the initial velocity is already given. So you could solve for v1 here from this by performing this integration. So essentially this represents the area under the curve on the left-hand side, and then this is the right-hand side for that, okay? So from that, you can do it repeatedly and create a plot. In the next example, given velocity as a function of position. So if you're looking for the curve of acceleration as a function of position, here's the form. So you have the velocity function, or the velocity function times the derivative of the velocity function with respect to time, okay? dv/ds. Okay, and the next example, this is actually example we'll work through the problem. Given the velocity as a function of time, here's the graph. So we have two functions that represent its velocity at different points in time, or different intervals of time. And we're going to look for the acceleration time graph and the position time graph over this time interval from 0 to 15 seconds. Okay. Okay, just looking at the solution for this. Basic idea, in this case, the acceleration is just dv/dt, so that's going to be the slope of this line, okay, which is constant. And also, you'll notice that this is also has a constant slope, so what our graph just turns out to be two constants, depending upon which time interval you're looking at, okay? So just dv/dt through 0 to 5 seconds up to this point. Here's the function. So just doing the derivative of this function is just going to come out to be 30 meters per second. Then we perform the derivative of the other function, essentially. So this part just goes away since that's a constant. And then we have just minus 15t. Do the derivative of that comes out to be minus 15 meters per second squared, okay? All right. So that's the first graph. The next one we're going to look at is position as a function of time. Okay, in this case, we're going to look to build a position versus time graph. And what we need to do is basically the opposite, or we need to do integration, perform integration in those two particular time intervals, okay, from 0 to t in this case, and then this case is going to be from 5, which starts here, essentially, 5 to t. So we have two separate integrals to perform, okay? The other point to keep in mind here is that you have an initial position, okay? And all you have to do is, plug into this initial equation with t equal to 5 seconds, which is right here, basically here. So initial position at that point, okay? Then you can this is done from whatever that position 5 to t, and then that gives you the actual function for position from here to here, so 5 to 15 seconds. So in the next problem, I'm going to look at determining the AT graph, the average speed and distance. So the average speed and the distance that you traveled between 0 and 80 seconds. So how far did you go, starting here and getting to here, the end, okay? All right. Okay, so for the acceleration graph, pretty straightforward. You have a velocity. Velocity is constant velocity, no acceleration. So of course that one has to be 0. Now in this case, you're decelerating. So you're going from essentially 10 meters a second down to 0, okay? So in this case, it's a constant slope. So we'd expect that we'd have a constant for the acceleration. And since, like I said, it's deceleration, you're going to find a negative sign. So for deceleration, you have a negative acceleration, okay? Okay, so determining the delta, in this case they define as delta S, or difference in position. So regardless of wherever you started, um, all it is essentially is going to be the area under this curve, right, up to this point. So it's 400 meters. You travel 400 meters in 40 seconds, okay? 10 meters per second, 40 seconds, 400 meters. The second part is now you're going to do the integral with respect to time of the velocity function, okay? So when you go and solve that and you put in the initial time is now 40 seconds, of course, and 40 seconds to 80 seconds and solve for this, you're going to come up with 200 meters. So the total distance traveled is 400 plus 200, 600 meters, okay? And now to determine the average velocity, you need to take that total distance and divide it by the total time, and that will give you your average velocity. And that's about it. So pretty quick section, some new concepts you need to look at. Basically, you're working with graphs or piecewise functions where they're represented with graphs.